Hello everyone, my talk is about neutrino mice and the early universe. I'm Bowen from the University of Southampton. First, let's take a view of the structure of the talk. During this talk, I will first tell you about the neutrino portal dark matter in the type 1 Seesaw model. We'll see the limitation of type 1 Seesaw model, which motivate us to study an alternative version of type 1 Seesaw model, which is called type 1b Seesaw model. Then in the framework of type 1 Seesaw model, we will discuss several cosmological problems, neutrino portal dark matter, resonant leptogenesis, and the vector portal dark matter. Okay, let's start with neutrino portal dark matter in type 1 Seesaw model. What I mean by neutrino portal is basically this term in the Lagrangian. It's a Yukawa type interaction between a dark scalar phi, a dark fermion chi, and the right-hand neutrino. The portal coupling is marked with small y. And the dark particles are charged under Z2 symmetry, which can stabilize the lattice one of them. And in order to simplify the study, we focus on a scenario which is called heavy scalar scenario. In such a scenario, the dark scalar is the heaviest one in the neutrino portal, and it can decay into a dark fermion and a right-hand neutrino, while the dark fermion chi is stable and can play the role of dark matter candidate. In the freezing production of the dark matter, there are three different processes involved. The first one is called neutrino Yukawa process. It's the scattering between the standard model particles mediated by a right-hand neutrino into a dark fermion and a dark scalar. The amplitude of this process is proportional to capital Y square times small y square, where capital Y is the Seesaw Yukawa coupling and small y is the portal coupling. The other two processes are the scattering between two right-hand neutrino into two dark scalar or two dark fermion. This process, the amplitude of this process are proportional to a small y to the power 4, which means it's completely depending on the portal coupling. In order to build a connection between neutrino physics and the dark matter, we are more interested in a case where the neutrino Yukawa process dominates dark matter production. And in order to realize that, we need a sizable Seesaw Yukawa coupling. Then let's see how neutrino portal dark matter works in a model called the Littlest Seesaw model. The Littlest Seesaw model is a very predictive version of type 1 Seesaw model with just the two right-hand neutrinos, and there are also some other theoretical considerations which can help us to reduce the number of free parameters. And by considering the neutrino portal dark matter in the Littlest Seesaw model, we found that in order to have neutrino Yukawa production dominating the dark matter production, we need the right-hand neutrino mass to be above 40 eV. It's not too bad, but still too heavy for the collider experiment to test. But things went worse if we take leptogenesis into account. If we want to realize produce the correct baryon symmetry, we need the right-hand neutrino mass to be the lattice right-hand neutrino mass to be around above 10 to the power 10 GeV, which is very heavy. And for such heavy particles, the gravitational production, which are the production mediated by a graviton, can be very important. Nevertheless, after considering all the things together, we can still find the region where the neutrino Yukawa process can dominate dark matter production. But it is very hard for the collider experiments to test that region, mainly because of the energy scale. And this leads us to a very natural question. can we find a model where neutrino Yukawa dominance can appear for GeV scale heavy neutrino and perhaps also compatible with leptogenesis? Then we found the new version of type 1 Seesaw model, which is called type 1b Seesaw model. In this slide, there is a comparison between type 1 Seesaw model and type 1b Seesaw model. The traditional type 1 Seesaw model can also be called type 1a. In the traditional type 1 Seesaw model, we need at least 2 Majorana right-hand neutrinos plus 1 Higgs doublets. While in the type 1b Seesaw model, we need 1 Dirac neutrino and 2 Higgs doublets. You see, this is because in the traditional type 1 Seesaw model, we have the Weinberg operator generated through this kind of Feynman diagram, involving a Majorana right-hand neutrino and one Higgs doublet. Well, in the Feynman diagram for the new Weinberg operator in the type 1b Seesaw model, we have 2 Higgs doublets involved. And in the traditional type 1a Seesaw model, we have 1 Yukawa coupling for each right-hand neutrinos. And in type 1b Seesaw model, we have 1 Yukawa coupling for each Higgs, which means that there is a conservation of number of Yukawa couplings in between these two models. And regarding to the frame parameters, after considering the neutrino mice and mixing, in the type 1a Seesaw model, there's only 2 free parameters. Well, in the type 1b Seesaw model, there are 3 of them, which means it's the type 1b Seesaw model. Well, it's less predictive than the Littlest Seesaw model, but it's still very predictive. Very predictive. And due to the expression of the light neutrino mice, the standard model neutrino mice in the type 1a Seesaw model, in order to have a sizable coupling, we need the right-hand neutrino mice to be above TeV scale in order to have dark matter production dominated by the neutrino Yukawa process. Well, in the type 1b Seesaw model, we have the 2 Yukawa couplings appear as a product in the expression of standard model neutrino mice. This makes it possible for us to make one of the Yukawa coupling small, while the other one is large, providing a GeV scale heavy neutrino. And through the large Yukawa coupling, the neutrino Yukawa process can dominate dark matter production. Okay, then let's see how neutrino portal dark matter works in type 1b Seesaw model exactly. Here is the particle content of the model. We have 2 Higgs doublets, 2 right-hand neutrinos, and a dark fermion, a dark scatter, and a dark fermion. The 2 right-hand neutrinos can form a Dirac pair, and the heavy Dirac neutrino couples to the two Higgs doublets in 2 different ways. And the portal the neutrino portal is in a similar form as before, just with a Dirac heavy neutrino. And also similar to before, the freezing production of dark matter involves 2 different class of process. The first one is neutrino Yukawa process, and the second one is dark sector process. And let's see some results. In the neutrino portal extension of type 1b Seesaw model, there are mainly 2 key parameters affecting dark matter production. The first one is the tangent beta. It is commonly defined in the study of 2 Higgs doublet models as the ratio of the wives of the 2 Higgs doublets. And the other one is the ratio of the dark particle masses. It is quite general for neutrino portal dark matter that if the mass spectrum of the particles in the neutrino portal is hierarchical. The dark matter production only depends on the ratio of the dark particle masses instead of individual dark particle mass. And in order to make a comparison with the collider experiments, we study we compute a quantity U square, which is very commonly used from the experimental side. It characterizes the mixing strengths of the stellar active stellar neutrino mixing. And after study all the three neutrino the mixing of all the three neutrino species, we found that the strongest constraint is coming from the mu neutrino mixing, which are shown in the plots above. In the figures, you can find some color dash lines. Above these lines, the neutrino cover dominance is allowed, while below these lines, the neutrino cover dominance is completely excluded for the corresponding condition. In the figure on the left, we fix the mass ratio of dark particles to be 1, while we change tangent beta from 10 to 30 to 60. As you can see, as tangent beta increases, the dash line moves downwards, which means the parameter space is less constrained. Well, on the right side, we fix tangent beta to be 10 and increase the ratio of mi from 1 to 10 to the power 4 to 10 to the power 8. And in this case, the color dash line moves upwards as the ratio of mass increases, which means the parameter space is more constrained. Then let's see how leptogenesis can be realized in the type 1 basis of framework. In order to realize leptogenesis in the type 1b framework, we consider an extended model of type 1 Seesaw mechanism with a super heavy third right-hand neutrino and a scalar field like this. Through the mixing with the third right-hand neutrino, the first two right-hand neutrino can get a mass splitting, and that means apart from the mass splitting, the two right-hand neutrinos the first two right-hand neutrinos form a Cauchy-Dirac pair. And at low scale, the type 1 Seesaw mechanism can be realized from this Lagrangian as this through this kind of diagram with the effective vortex here. And in the figure on the right, we show the result. For leptogenesis, the region for correct leptogenesis will be produced in the region shadowed with yellow. So as you can see, the yellow region where the resonant leptogenesis can be realized overlaps with the region where the neutrino the neutrino cover process can dominate dark matter production, and it's also within the sensitivity of future collider experiments like SHAPE and FCCE. Okay, finally, let's talk a little bit about vector portal dark matter in the type 1b Seesaw model. So in the type 1b Seesaw model, if we consider a U1 gauge extension of the type 1b Seesaw model, we'll find something fancy. well, because in type 1b Seesaw model there is a Dirac neutrino, it can be charged under gauge symmetry without breaking the gauge symmetry. It is not possible for Majorana neutrino because it will naturally the Majorana mass is naturally non-compatible with with any U1 gauge symmetry. Then we can extend the model with a dark scalar, dark fermion chi, and a scalar phi, which breaks the U1 symmetry, which can get a y1 whose y breaks the U1 symmetry, U1 prime symmetry, and the dark fermion is has a half integer charge. It's the only particle have a half integer charge under the U1 prime symmetry, which means after the U1 symmetry breaking, there will be a Z2 symmetry. There will be a remaining Z2 symmetry, under which only the dark fermion chi is charged. And in this case, because the gauge coupling is usually sizable, we consider the freeze-out production of dark matter. It can be the dark fermion can be produced through the scattering of the heavy neutrino or the scattering of the Higgs doublets mediated by the right-hand neutrino, mediated by the U1 gauge boson Z prime. And here is the region where the correct radical abundance can be produced. So, in summary, the type 1b Seesaw model have the following features. First, there's only 3 frame planters after considering the the neutrino mass and mixing, and due to the expression of the structure of the type 1b Seesaw model, it allows connection between dark matter and neutrino physics through neutrino portal with a GeV scale heavy neutrino. And we have also seen that the resonant leptogenesis can be realized in an extended model. And finally, due to the direct nature of the heavy neutrino, it can be charged and under a U1 prime gauge symmetry. Thank you for listening.